In Chapter 6, we are going to be exploring exponential and logarithmic functions. We are going to be starting with exponential functions. So let's get started with 6.1. So there's some formulas and some facts that we need to know. The first terminology you're going to hear me talk about is exponential growth. Exponential growth is an increase based upon a constant multiplicative rate of change, where exponential decay is a decrease based on a constant multiplicative rate of change. And this is kind of the general formula for any exponential function. Now let's analyze what you're going to see with that formula. If your A is positive, that's a good indication that's an exponential growth or decay. If the B is a number greater than 1, it will be a growth. Your A is your initial amount, your starting amount, whether it is bacteria, amount in an account, a population of any sort. So that's what we're talking about for a growth. For a decay, you're still going to have a positive number, but in this case, this number here is going to be fractional. And you might notice that our x is the exponent, hence the word exponential growth or decay. So let's first just practice identifying what an exponential function is. So this first one here, we have a base, we have some function of x as an exponent, so that one is an exponential. This one is not. The x is not our power, it's not up in as the exponent, so that's a no, that's a polynomial. Our third one here, our h function, you'll see this is a function of x. Now, as long as this number is a positive number, like here we had a positive 4 base, here we had a positive 1/3 base, that would be considered an exponential, yes. Now, the problem with j of x, it almost looks like an exponential. We have a x in our exponent location. But because of this negative here, this is actually a type of oscillating function. It goes from positive to negative and positive to negative. And so, no, that would not work. So you have to have a base. Now, you could have a negative in front of the 2 to the x, but that's a different type of exponential function. Now, let's practice using our exponential functions. So here we have an f of x and a g of x function. Let's use each one of them. So in our first one here, we are going to plug 2 as our input into our f function. So that's going to be 5 times 3 to a power of 2 plus 1. Now let's remember our rules of order of operations. Let's plug or simplify the power down first. And the rule is we have to do exponents first before any multiplication. So one of the most common mistakes I see students make is trying to make that a 15. And that's not. That's really 5 times 3 cubed is really 5 times 3 times 3 times 3. So you want to make that a 27 first, and then you want to multiply 5 times 27 for an answer of 135. Now, in B, when we plug -1 in there, same thing. We're going to put -1 where the x is sitting. We're going to simplify the power, and then we're going to do this location first. Well, anything to the 0 power is always 1. So that's 5 times 1, or 5. So you'll notice that the 5 just multiplies by the answer of whatever that thing to the power is. Now let's go ahead and use our g function. So this time in C, we're going to plug 3 into our g function. So this is really 8 times 1.2 to a negative 2 power. So watch how that you enter that into your calculator. So you're going to enter your 1.2 to a power of negative 2. You can get that answer, and then you multiply by 8. Now, if they did not specify, please go out to the nearest hundredth, 2 decimal places. This one actually is 5 5/9 if you wanted an exact answer, or if we rounded it to 2 decimal places, that would be 5.56. So that is how we use a function that is an exponential function to plug some values in. Now, one of the most common things we're going to be seeing in the exponential chapter is this number e. Now, we're very used to the number pi, that irrational number, 3.1415926. This is the irrational number e. It is 2.71828. Most calculators have that number, will be somewhere that you can access on your calculator. But let's actually practice. Now, I'm sorry, this one looks kind of funny. That is e to the 1/2 power. So if you hit the second button on at least the calculators I have in my room, and then you put to the 1/2 power, that is really the square root of 2.71828. And if we go again to 2 decimal places, that's 1.65. So make sure that you know how to enter that into your calculator. So if you have a calculator, try it. Okay. Now this is really e to the negative 1. Now that's really just the reciprocal of e. If you flip 2.7, that's 1 over 2.7. So we should expect to get a decimal value here, rounded to the nearest hundredth. That's 0.37. And then finally, e squared, that's really just that 2.71828 times 2.71828. But the more accurate you can be if you use that actual e button, then don't round until you get a final answer. And our final answer is 7.39. So, just make sure that you know how to access that on the calculator. If you don't have an E show up on your calculator, show me your calculator. I might be able to help you, or just use 2.71828. So there you are ready to take a look at these. Now I wanted to also talk about 14 through 17, and so there is a little piece of information I want to relay. So if you could write this down for me. So we're going to be exploring eventually some functions, some kind of like real life examples, some exponential functions that look a lot like the formulas that you see right there. If we add on a rate, that's going to be a growth. And the reason that is because if our rate is, say 2%, that would be 1.02. But if we subtract off the rate, so if our rate is a 2%, but it's declining, or it's a decay, we are going to be subtracting. And so our base will always be some positive number between 0 and 1. Okay? So I just want to discuss 15 and 17. It says, determine whether the equation represents an exponential growth or an exponential decay, or neither. So if we look at 15 and 17, since this number here is more than 1, this is considered a growth. It's growing by 6% for whatever time frame they're using. But since this one is a number right here, less than 1, it's actually 1 minus 3%, or 1 minus 0.03. The rate is a 3% decline. This is a decay. So if you ever see this notation here, so this particular real-life application, you started out, let's say, with 220 bacteria. It's going up by 6%. It's growing by 6% every hour. That's the formula represented there. But this might be, let's say, a population of a city. This little small city has a population of 11,701. It's going down by 3% every year. So that's an example of a decay. Now for 44 and through 50, you are just plugging into the function using your calculator, rounding to 4 decimal places. Now let's talk about 6.1, some of those word problems we were talking about. So this is an example of an exponential growth. You'll see it has that plus there. P is our initial amount. R is the rate of increase. Usually they're going to give that as a percent. So if they give it like to you as 4%, just move that decimal place 2 over to the left to find the correct decimal. And then the time is how much time has elapsed. So this formula is really important. So it ends up being plus the rate if we are growing exponentially. It is minus the rate if we are declining exponentially. So if we look at this problem, it says India's population is 1.25 billion in 2013. It has an annual growth rate of 1.2%. What would the population be in 2013? So let's go ahead and write down, I'm just writing down this formula right here. F of t is P times 1 plus r to the t, okay? Now let's identify what we know. The initial population is 1.25 billion. The rate of growth is 1.2%, but let's change that to 0.012. Okay, now if we change that to 0.012, let's plug everything into the equation. So our P is going to go here. Now you can just leave it 1.25 as long as you tack on the word a billion, or you have to make sure that you see 9 places for the billion. Okay, and then 1 plus 0.012, and t gives us the following equation to calculate the population of India. Now, the question said that was the rate in 2013, and from 2013 to 2031, that is an 18-year difference in time. So the time that's elapsed is 18. So what do you get when you plug in 18? Well, if we plug in 18, we get 1.25 billion times 1.012 to the 18th power. Now, I would not round anything until the end. And these are people, so, you know, I would keep it to the nearest whole number if it's a person or a bacteria or something tangible like that. If it's money, I would probably go to the nearest penny. So let me just write this down, and then I'll put the commas in once I'm done. So that would mean that we would have 1.5 billion by 2031. So you could even label that as people. So let's do another one. It says in 2006, there were 80 deer in the park. By 2012, the population had grown to 180 deer. Find an equation to model the growth of the deer population over time. So we're going to call that 2006 time 0. So at 0, we had 80 deer. Okay, so this would be your time. This would be our total population. Now let's write down that formula. Okay. Now, if we plug 0, 80 in, watch what happens. So at time 0, we get an answer of 80. So 80 equals P times 1 plus R to the 0. Now what's great is anything to the 0 power is always 1. So I know that P is 80 because this is equal to 1. So now let's kind of revamp our equation a little bit. We know that this is our equation, and we need to find an equation where the R is sitting there in the correct spot. So now, how much time has elapsed from 2006 to 2012? Well, that's 6 years, and our population is now 180. So now let's plug that into our equation. So 180 equals 80 times 1 plus R to the 6th power. Okay, now we're going to divide both sides by 80. So we get 2.25 equals 1 plus R to the 6th. Now, I hope you realize that, well, how do I get rid of a 6th power? That would be a 6th root. And most calculators allow you to do that. So if we take the 6th root, you'll see that one that has a radical with an x by it. So you hit 6, and then that second button, and there should be like a little x before the radical. And we get that it's 1.1447. And I'm going to take it out a few decimal places, and then just subtract 1 from both sides, and we get that R is 0.1447. Let's call that 0.145. Now, as a percentage, our rate then is 14.5%. So now what we're going to do is we're going to go back to this version of our equation, had everything in it except our R. So we're going to put this R in there, and then we got our equation. So our answer is f of t is 80 times the quantity of 1 plus 0.145, which is 1.145 t. And you can see that's kind of what 1 plus R was right here. So that's what should be in your parentheses. That is the equation that will model the growth of the deer population. So that is our answer. So we're going to stop there, and we will continue this next video, next class. Thanks.